Yes, you're audible.
Oh, So let's start with maxima and minima today. First of all, before starting maxima and minima, uh, I would like to tell what are some common technical terms, and those terms I will describe through a graph. And through graph, I will also illustrate some examples where you can observe the patterns of the graph, like either the graph is increasing or decreasing or constant, right? And you know how these graph looks, or if you forgot how can how are the what are the possible shapes of these kind of graphs. So let us revise that also. So let's consider this a function fx whose graph is given to us. All right, and graph is somewhat like graph moves like this. Yeah. Let's take this graph as this is a graph of some function y is equals to fx. Right. These are x-axis and y-axis, and I would like to show you some things here. So first of all, let's start with this. Let's say the graph is defined from this point. Let's say this point is so this point is x is equals to a, and graph is defined up to this point, which is x is equals to b, and this is a graph of some function y is equals to x. Right. I would like to show you some basic things here. How can you observe the graph using increasing and decreasing function? And what are the uses of increasing and decreasing function? So first of all, let's consider this point. So at this point, roughly at this point, this particular region, which starts from A up to this point. Okay, let's choose these some of these points first of all. And I will tell you what are these points called. I mean, what do you call these points? And then what are the how can you understand these points? This is not say this is this. This is smooth, right? Okay, so these are some points which I would like to show you. One is this, one is this, one is this, and one is this. Let's call them A, B, C. Now, why did I mark these points? You can intuitively, first of all, see, or you can just logically see that these points are the peaks, right? Either the upper peaks or the lower peaks, right? Or if mathematically you want to understand what are these points, so these are the points we call extreme points. Extreme points mean either you can call them extreme points or you can call them point of maxima or point of minima. One will be point of maxima and one will be point of minima. No, just give me a minute. Yeah, sorry guys. Yeah, let's start with this. Yeah, so we have defined these 4 points A, B, C, and D, right? And we know what intuitively I can see that these points are the peaks, either upper peaks or lower peaks, and mathematically I can see, I can observe these points like at point A. If you observe the value of this function, money, the value of y, this, sorry, this, right, is highest, right? But at this point, corresponding to this x, whatever this x is, right? Some x will be there. Let's say this is x1, then there will be a y1 to that, and this value of y1 will be greater than its neighborhood. Greater than its neighborhood money, all the points in the neighborhood of A will have a lower y value, right, for this graph. You take any point, either towards the right of A or towards the left of A. You take any point, right? And if you find out y, the value of y or the value of the function at that point, that will be minimum than this y1, right? So this point can be pointed as a local minima, a point, which gives you the highest y value in the neighborhood of itself. A point which gives you highest y value or highest output in its neighborhood is known as local maxima or point of maxima, right? Similarly, you can see this point B, or either you can see this point D. So these points are, first of all, what are these points called? A, B, C, and D. These points are known as uh, extreme points. Extreme points. Or extreme points, बोले या फिर turning points. You can also call them turning points. Because the graph is turning, you can clearly see one more important property which all of these points exhibit. That is that at every point A, B, C, and D, the graph turns. Right? You can check at A, the graph was moving towards upwards, but after A, the graph is moving downwards. Right? And similarly, after B, the graph is again moving upwards. After C, the graph is again moving downwards. After D, the graph is again moving upwards. Right? So we can also check the direction that the graph is turning. At all of these points, the graph is turning. Right? That is why we are calling them extreme points or turning points. Extreme points because the value of y, the value of output is extreme. And extreme money both maximum also and minimum also. Either these points can be point of maxima or these points can be points of minimum. Points of minimum money, that value of y you obtain at B will be lowest in its neighborhood. And neighborhood money, this neighborhood. By neighborhood, we mean this region, right? Which the points which are surrounding A, towards the right also, towards the left also. So these points, we are talking about these points, right? These points. So in all of the neighborhood of A has highest value. That is why you can call A and C as local maximum or point of maximum. This A also and this C also. And similarly, B and D can be known as local minimum or point of minimum. So very simple definitions. Now these 4 points are known as extreme points or turning points. And we know that by turning point or by extreme points, we only mean either these points can be local minimum or these points can be local maximum. By local minimum, the value of function at these points will be lowest. By local maximum, the value of function at these points will be maximum in its neighborhood. Whenever we are saying maximum and minimum, we are saying in the neighborhood, right? These points are local minimum and local maximum. Now, if no, let's talk about why we are finding, why are we interested in this, right? So this function y is equals to fx, we want to know its maximum output and its minimum output. For example, this y is equals to fx can represent a revenue function. So we want our revenue to be maximum, and to get our revenue maximum, we will be plotting some graphs on some variables, and if we see that this will be the optimum value to use, right? We want to operate at this value, because at this value, the value of the whole function is at its highest, right? The value of from starting from point A up to point B, this particular value C is the highest, right? These points, yani ki point C and point D, I'm particularly talking about point C and point D, right? So point C, so you can consider them as goons, right? Goons mean these are like local goons, A, B, C, D. Everything which is done in its neighborhood is can be called as, can be termed as local minima or local maxima. But out of all the local minimas and all the local maximas, right? Along with all the 4 points, all the 4 extreme points, along with the 2 points from which your graph is starting and at ending at, right? All these 6 points will be considered for 2 values. For 2 values, we want to find out the absolute maximum. But we want to find out the maximum value, at max, what can fx achieve at max, and we want to know what can be the minimum value for fx, absolute minimum value for fx, right? So these points are known as absolute point of maxima, right? And so there are 2 concepts here. One is local minimum, and second is absolute minimum, right? I mean, absolute minimum or absolute maximum. Absolute minimum or absolute maximum means the function, the value of the function at its lowest and at its highest. But a local minima or local maxima can be if a point is highest in its neighborhood, then it can be termed as local maxima. For example, A and C both are local maxima, right? A and C both are local maxima because both are giving us maximum value in their neighborhood. But C is called as absolute maximum, absolute maximum or absolute maximum value, right? So just give me a minute, guys. I would like to. Yeah, we're given first rotation. Yeah. Okay, correct. Sorry, D is absolute minimum. I just wanted to look at one year syllabus. What are the topics that we
So
need to
what's the
cover?
difference between local and absolute?
Absolute maxima, like for example, C, absolute maxima will be the point at which the function fx will attain its highest value. I mean, in all the interval from starting from A up to B, up to this point, B, right? starting from A up to B, the point at which fx will be highest in all of this interval. जहां पे भी fx मेरा सबसे ज्यादा वैल्यू ले रहा होगा. अभी A अपने नेबरहुड में सबसे बड़ा है, ठीक है, कूल है. C अपने नेबरहुड में सबसे बड़ा है, कूल है. तो दोनों को मैंने बोल दिया लोकल मैक्सिमम. सिमिलरली B और D अपने नेबरहुड में सबसे छोटे हैं, अपने आस पड़ोस में सबसे छोटे हैं, तो आई एम कॉलिंग देम एज लोकल मिनिमा, राइट. बट अब मैं अगर अपने फंक्शन की एब्सोल्यूट मिनिमा या एब्सोल्यूट मैक्सिमा वैल्यू बोल रहा हूँ, तो इसका मतलब मैं जानना चाहता हूँ कि फंक्शन की हाईएस्ट वैल्यू कौन सी होगी, किस पॉइंट पे होगी, और फंक्शन की हाईएस्ट लोएस्ट वैल्यू किस पॉइंट पे होगी, ओवरऑल स्टार्टिंग फ्रॉम ए अप टू बी. So if I'm talking about absolute maximum, then absolute maximum माने the point or the value of y at which fx is overall highest, right? There should be no other point which has a higher value than c, not just in its neighborhood, in all of the function from whatever is your observance frame, but in all of that function, your c must attain the highest value, right? That is the difference between absolute and local. Local is in its neighborhood only, and when you are talking about absolute, you're checking on a big interval. Did you understand it? Tarif.
Yes, sir.
Okay. Sure, then let's start with. So this was the basic introduction. Like, what are we going to do? So we want to find out point of local minima and point of local maxima. Now, also observe one more thing. See, from point A, small a, up to capital, right? The function is increasing. No? Function is increasing. And then the function is also moving rightwards as well as upwards. So as you increase x, your y is also increasing. But when you move from capital A to capital B, function is decreasing, right? So first your function increases and then it decreases. When it happens, consider what is the situation. First of all, consider the scenario. Your function is first increasing, it increases up to a certain point, right? And then it starts decreasing. If my function is increasing and then reach up to a certain point, and after that it decreases, then that point must be local minimum, local maximum. No? I mean, my function is increasing, and then after reaching to a certain point, it starts decreasing. So that point after which it starts decreasing should be local maximum, should be local maximum value in its neighborhood. Because before that, you were lesser, and after that point also you are lesser, because before that you were increasing. So increasing तो थोड़ी देर पहले हम कम थे, थोड़ा और आगे बढ़े तो ज्यादा हो गए, right? And after this point you are decreasing. मतलब whatever you have right now, you are only going to decrease, right? So when this happens, that your function is increasing and then decreasing, then you get a local maximum. Similarly, if your function decreases first and then increases, then it gives a local minimum. No? Did you get this, everyone? Very simple concept. If your function first increases and then decreases, you get a local maximum. If your function first decreases and then increases, you get a local minimum, right? Okay. Chalo then, let's start moving towards some basic pandas. You can also note this down just for your simplicity. So these are the points at which fx is highest in its domain. Whatever its domain is, whatever values you can give to your fx, c will be the point at which fx will be giving you highest value at all the axes. If you consider all the axes, then c will be that point. C will be that value of x and y where you will get the highest y. right? And D will be the point at which you will get lowest value. There will be no other point than absolute minimum, which will have a lesser value than absolute minimum. Right? Okay. Okay. Also note down this definition. What is point of maximum or local maximum? Fx is highest in its neighborhood. And Fx is so these are the two most important things and will be very crucial in understanding uh, about these extreme points. But before we move to the main concept, to the main crux, which is absolutely related with the concept that we have just discussed. But before we move to that, I would also like to tell you about one more point. Okay? So this point is known as not right now. Let's talk it about a bit later. So before that, let's understand how to find out, first of all, a maximum and minimum point. I mean, how to find out these extreme points. And then if you find out extreme points, then how do you check whether that extreme point is point of local minima or point of local maximum, right? Chalo, but before that, yeah, is a good thing which they have shown in some graphs. So they have used some graphs in NCRT. Let's consider these basic functions and let's consider about these maxima and minima. And let's also observe some things which I would like everybody to understand. So these are some illustrations. First of all, this is the graph of fx is equals to x squared. Fx is equals to x squared looks like this. Right? So can you tell me by just understanding this graph that is there an extreme point first of all? And this, by the way, this increases up to infinity, and this also increases up to minus infinity. Okay. So can you tell me if there is an extreme point in this graph? I'm not asking you which point is it, but can you identify if there is an extreme point? There must be an extreme point, no? This point, somewhere around this. Okay, so the graph is not good, but I mean, the graph is not perfectly labeled, but in spite of that, you can easily understand this. Tutor. Undefined maximum. Oh, no. We don't say about the points which we can't see. So there is no point of, we can't talk about point of maximum actually, because I mean, we don't. Oh, this is too bad. Yeah, this is y-axis, this is x-axis. And this now somewhat is to a close figure, which y is equals to x square is. So this is y is equals to x square. And this point, you can observe that before this point, the graph is, you can see, if you are coming from this side, then the graph is decreasing, right? Because you are moving towards side, but the graph is going downwards, right? But after this point 0, if you see, you move here and the graph is upwards. So it is increasing. But on this side, this is decreasing. Right? So after decreasing, the graph increased. So it must give you a point of local minima. And you can observe, guys, clearly. We also know that y is equals to x square gives us the minimum value at x is equals to 0. If you put x is 0, then y is also 0. Otherwise, in every other case, your y is equals to x square will give us some value. You put x anything, you will get some value, which will be positive, obviously. So y is equals to x square has a local minimum, or in fact, absolute minimum. This local minima is its absolute minima as well. There is no other point on this graph which has a lower y value than origin. Origin is the only point which has x is equals to 0 and y is equals to 0. Other than this point, all the other points on the graph has a value greater than 0. So this is point of local minimum. You can see that after decreasing, the graph has increased. So if somebody asks about the point of extreme points in fx is equals to x square, this is very easy. Extreme points is only one, which is x is equals to 0. And at that point, you get your fx or f0 as 0. Rather than that, you can also write y is equals to 0. Y is equals to 0 is the minimum value of the function. And x is equals to 0 is the point at which you get your minimum value. Right? So this is the minimum value of function. Minimum value of the function. And this is point at which, or point, either you can call it point of minima, or you can also call it as point at which local minima exist. Or in fact, global. You can also call this global, not, I mean, local is not global, but global is exactly equal to absolute. This is also your global maximum, sorry, global minimum. Global is a word used for absolute. You can either use absolute or you can use global. I forgot to write here. Just give me a minute. Yeah, so this is also known as global minima or global maxima. So this is the point which is also a local minima and also local global minima, right? So x is equals to 0 is the point at which global minima exist, and y is equals to 0 is the minimum value of the function. Right. So if given graphs, you can very easily obtain the minimum and maximum values. All the local minimas, all the local maximas will be very easily obtained, and you can see these examples. Let's take one more example, which is fx is equals to mod x. Okay, I'll also tell you some other examples. Sure. First of all, let's take fx is equals to mod x. Yeah. Let's start with fx is equals to mod x. This is, we know the graph of a modulus function is V-shaped graph, right? The graph of modulus function. And this V-shaped graph is decreasing on x less than 0 and increasing on x greater than 0, because at these points, all the points which lie in the second quadrant are like this. If you move rightwards, then the graph is coming downwards. So this is decreasing. And then here you can see that the graph is increasing. So definitely it must give you one point of local minima, and which you can observe intuitively as well, that this point has the lowest value of y, because other than that, every value of y is positive, right? The graph only exists in first and second quadrant. First and second quadrant one, y is positive. Hence, this particular graph also has a local minima, which is also a global minimum this time. So we must write it like this, not like local and global minimum. And it exists at x is equals to 0, right? So at x is equals to 0, mod x or y is also 0. This is the lowest value, right? And this is the point at which lowest value exists, right? But also it is not necessary for every function to have a local minima or local maxima. I mean, this is a very important property to extract the extreme points from all the functions if they exist. But if there is not a extreme point, or there is no point of local maxima or local minima, or it can also happen that I mean, one point of local maxima is present, but there is no point of local minima. For example, you can observe in first and second case, you have point of local minima, but you don't have point of local maxima, right? You don't have point of local maxima. While in the first example, in the very first example, when we try to understand what are the concepts, we had local maxima and local minima both, as well as absolute minima or global minima and global maxima as well. So it is not necessary to have these points, but if you have if you have a function which contains local minima and local maxima, then it becomes very important to understand them and extract these points so that uh, you can optimize your solutions, right? And we will see the application of this in the later part of the chapter. But before that, let's try to just understand the concept and with some basic examples, right? So let's also understand some cases where there is no global minima or global maxima, or rather local minima or local maxima. So right now, I mean, in the whole chapter, we will only talk about local minima and local maxima. This global minima, global maxima works same as local minima and local maxima, but the only difference is that they will have the highest value, right? There will be multiple local minimas or local maximas, but there will be only one absolute minima or absolute maxima, right? This is the only difference. So we'll be mostly talking about local minimas. Whenever I say minima, I mean a local minima, or whenever I use a word maxima, then it will certainly mean local maxima, right? So let's start with another graph, which is, another function, which is greatest integer function. We have discussed this at some point, but if not, then try to understand this graph. This is greatest integer function, and I have already told you what is the function of greatest integer function, right? If you give it some value, then it returns an integer. Now, what are the rules to convert that value into an integer? So let's say if I give GIF integral value, right? For example, 5, then it will return me 5 itself. Right? Because the job of GIF is to return me an integer. And if you're already giving me an integer, then it has nothing to do on it, right? Because the intended job of GIF is to make everything an integer. But if you're already providing an integer, then what else to do on this, right? The job is already done. Now let's start with another example. Now I have a decimal 5.2. What happens if we are not providing an input which is integral, right? So in this case, 5.2, what happens is you will get the integer which is just lesser than that quantity. So 5.2 se just chota integer will be 5, right? So this will be the answer. So for example, 5.99, still 5. You can understand greatest integer function as the greatest integer which is less than or equal to that value. Greatest integer which is less than or equal to that value. So 5.99 say you have to find out the largest integer which is lesser than 5.99. So largest integer which is lesser than 5.99 is 5, right? 4 will not be the largest integer which is lesser than 5.99. 5 should be the largest integer which is lesser than 5.99. So the answer is 5, right? Similarly, 6.62 will be. Can somebody answer this? What is the GIF of 6.62? 6, right? Cool. And you also know about negative integers, right? Don't get confused in negative integers. So let's tell me this, minus 1.27. What is the GIF of minus 1.27? Minus 2, correct? Yeah, good. So GIF works like that. Now, I have already told you about GIF though, but we have not proved how can we draw this graph, right? Now today I would also like everybody to show how we can draw the graph of fx is equals to greatest integer function of x, because see, we have discussed one time about these functions which are expressed by multiple expressions, right? Some functions are expressed by only one expression. For example, fx is equals to x squared, or fx is equals to sin x, right? But there are some functions which are expressed by multiple equations or multiple expressions. Can somebody tell me what do we call these functions which are expressed by multiple terms, multiple equations? Come on, someone. लिखा है यार हमने. Just give me. Correct, Shavis. Very good. Very good. Piecewise functions, right? So these kind of functions are known as piecewise function. For example, fx is equals to mod x is also a piecewise function, if you remember. This can have two values, either x or minus x. X when x greater than equal to 0, and minus x when x is less than 0. In the same way, this greatest integer function can also be defined. How it can be defined? So, for example, when x is in between 0 to 1, you have to break this x into multiple cases to define the function. You have to break the domain, or you have to basically break the domain of x at every point where the graph is discontinuous. Now, this graph is not continuous, first of all. Just give me 2 minutes, guys. It will be very fast. Just give me 2 minutes. Yeah, am I audible?
Yes, sir.
Okay. Yeah, guys, I'm not well today, so that is why I have to take breaks because I have cough and yeah. So fx is equals to greatest integer function of x is basically defined on multiple values of x. We have to break x at every point at which the graph is discontinuous, and the graph is discontinuous at every integral point. And why is happening that? Let's observe the values of greatest integer function of x between 0 to 1, when x is in between 0 to 1. So let's say when x is 0, when x is 0, fx is also 0. The value of y is also 0, right? When x is 0.1, the value of y is also 0.1. Whatever your x is, that comes directly out of this greatest integer function when x is in between 0 to 1. Let's say x is 0.7. When x is 0.7, when x is 0.7, right? So your f 0.7 is nothing but 0.7, right? Your whatever your x is, whenever your x is in between 0 to 1 in this particular interval, whatever your x is, your y has the same value, right? Because if you put fx in this and x has value 0.7, then the GIF of 0.7 is 0.7. Oh, sorry, my bad. Oh, my bad. I was explaining actually fractional part of x. My bad. What should be the GIF of 0.7? It should be 0. No, GIF of 0.7 must be 0, right? So in between 0 to 1, the greatest integer function of x is 0. Whatever your x is, when x is from 0 to 1, whatever your x is, y has the same value, 0. Because the largest integer that is smaller than these values is 0. Okay? Similarly, this will be -1. This will be 1. From 1 to 2, your GIF will take only 1. The answer will be 1 every time. Yeah. So this is how you can draw your graph of greatest integer function of x. Yeah. So now the graph of greatest integer function of x will look something like this. When x is from 0 to 1, the graph is this. From 0 to 1, the graph is this. Okay, let me use this pen. At 0, the value is 0, but at 1, the value goes back to this point. At this point, there is a hook. Right? From 1 to 2, and so this is 1, and this is 2. So from 1 to 2, this goes like this, and then at 2, this reaches to this point. Right? This is moving like this. This is also known as stepwise function because these are there are steps which are forming here. You can observe this. Yeah. So, and this graph is constantly moving in stairs. Like this. Now you can observe. So there is no point of minima or maxima here, right? Because this is constant. This is a straight line, which is horizontal, which is parallel to x-axis. This is a straight line. No increasing, no decreasing. As you are moving rightwards, right? Your graph is same. For a particular line, your graph is same, right? So no local minima, no local maxima. So my point is that your graph can be anything. I mean, there may be a graph which has no local minima or which has no local maxima, right? But now let me pose a different question. Let me pose a different question to you also. What about if I say, what is the maximum? Let's say the question is this: what is the maximum, or let's say, what is the global maximum or global minimum? So you will say that we have no, I mean, you will say that we don't have sufficient evidence here. We don't have sufficient evidence here to comment on global maximum or global minimum. Why we are saying that? Because see, this will be increasing, right? So what are the values that greatest integer function of x can achieve? It can achieve 100, 1000, 1 lakh, right? 1 crore. So this will keep increasing. At some point, do we know the highest integer? No, right? So there is no global maximum or global minimum. Does not exist. You will say does not exist. Does not exist. Now, if the question is, what about local minimum or local maximum? What about local minimum or local maximum? Then the answer will be, it depends. Okay? Depends. Depends on what? Depends. What are you? What is your question? So if you ask me, so if the question is this, let's say the question is this: what is the minimum and maximum value of y is equals to greatest integer function of x in x belongs to 2 to 7.5. Right? So the question, the question changes now. We do have an answer. Why? Because we are limiting x. We are posing a condition on x domain. We are limiting our x values. If you are limiting our x values, it basically means that you are also limiting your y values. And in those limitations, there can be a minimum and maximum value, right? In those limitations, there can be a minimum and maximum value. You can easily understand this through this example only. So in this, you can observe the graph from 2 to 7.5. So it starts from 2. It takes the point 2 into account. So it starts from this point, right? It starts from this point. And it moves up to 7.5. Now we know that at 7.5, the value will be 7. And from 7 to 7.5, the value will be 7 actually. And from 6 to 7, the value will be 6. So we know the highest value of y now. So y minimum is equals to 2. And y maximum is equals to 7. We have an answer. Okay? So it depends. What is the question? If you're asking about minimum or maximum values in a certain interval, then we will definitely, we can have an answer for that. And in most of the cases, we will have an answer for that. But when we are talking about global maximum, global minimum, for some functions, it may exist. And for some functions, it may not exist, right? Now, how do we know? First of all, we don't know the graphs of every function, right? The functions can be really complex. These were some of the easy functions which were easy to draw. That is why we have drawn these graphs, but it will not be possible every time. Right? We do know that. So what is the short way to look for extreme points? How do we find out these extreme points? How do we first of all know whether there are extreme points or not? And if yes, then what are those points? How do we find them? Right? This should be the objective. But now let's understand one thing first. How can we find this? How can we find out extreme points? So to find out extreme points, we can use this concept actually. We can use this graphs that when an extreme point occurs, the functionality changes. Functionality changes, man. Matlab, function was increasing before that point, and then after that, function turns itself. Just give me a minute. So the crux of the whole idea is that the function changes or function turns itself. Turns itself money. If the function was increasing, then it becomes decreasing. And if the function was decreasing, then it becomes increasing. Whenever it passes through an extreme point, right? And that is why we are calling them extreme points, by the way, turning points, right? So for this, what can we do? We can check about the signs of f dash x. If f dash x is positive, right? If f dash x is positive, it means that the function is increasing. And if f dash x is negative, it means that the function is decreasing, right? So we can check for the signs of f dash x, and that would result in telling us like what are these points of local maxima or local minima, whether they exist or do not exist, right? So if let's say your function is only increasing, then it will certainly not give you any local maxima or local minima. If your function is only increasing, because it only increases, it does not decrease. It is not changing its sign, right? F dash x is not changing its sign. F dash f dash x is positive for the whole values of x, right? So this is very important to note here as well. How do we find out? So the question is, how to find out extreme points? Important question like this. So to counter this problem, our first argument is that f dash x changes sign. These are known as turning points. Turning points mean f dash x changes signs. Why changes signs? Either decreasing to increasing or I to d, increasing to decreasing. Okay. Your function becomes either from decreasing to increasing or increasing to decreasing. That is why the f dash x sign changes, right? So it means check for the signs of f dash x. If it changes, what does that mean? If the sign of f dash x is changing, it means that there lies an extreme point. Extreme point exists. If it changes, then extreme point exists. Now, how do we find that out? So for this, we already know. Give me a minute. Yeah. So so how do we check? To check, we have to to check for the extreme points, we have to find out f dash x and then check whether the sign of f dash x is changing or not. And how do we check that? By the way, use what? Wavy curve. Use wavy curve. Use wavy curve. So, and this method, by the way, is known as your first derivative test. We will also understand second method, which is known as second derivative test. But before that, we are learning first derivative test, which is basically based on your a key insight that extreme points only exist, or extreme points money, your graph changes its direction, and your graph changes its direction money, the sign of f dash x changes, because if it was increasing before, it changes to decreasing, and if it is was decreasing before, then it changes to increasing. So sign of f dash x changes. So first derivative test says that you find out f dash x, check whether the signs of f dash x are changing or not. If the sign of f dash x is not changing, it means that if either your f dash x is positive or either your f dash x is negative, then in both the cases there is no extreme point. Right? There is no extreme point. But if the signs of f dash x are changing, then there lies an extreme point, and to find them out, you use wavy curve. Right? You use wavy curve. Extreme points can be directly obtained from wavy curve. Right? And let's also try to establish two fact here, that if it changes, so let's start with a first. Let's say the function was increasing before, consider y is equals to fx, right? And it was first increasing and then decreasing. If it happens, first increasing and then decreasing, so you get a graph like this, first increasing and then decreasing, right? It means that you get a point of local maximum. Yeah? And if fx was decreasing first, but after passing through the turning point, it turned to an increasing function. It turned to the it means that the graph is somewhat like this. And this is the point you're talking about, which is local minimum. Okay. Now let's try to use Fatafat say first derivative equation. This is easy. We'll be able to solve this number. The only difficult part in this particular exercise is how to handle word problems. But before that, you have to be extremely good in these portions, what we are talking about right now, because this will be extensively used, and also this particular exercise will contain around 6 to 7 marks for your board exams. There will be a definite question from this exercise. Yeah, and also one more important fact before we move forward, which is basically this, that if a function 2i is equals to fx is monotonic in nature. Now, first of all, what is monotonic? Monotonic is either only increasing or decreasing. Either your function is only increasing or your function is only decreasing. It is not like it's increasing as well for some portion and also it's decreasing for some portion. Yeah. So if a function y is equals to f dash, fx is monotonic. Monotonic means either it is increasing for the whole domain or it is decreasing for the whole domain, which basically means that f dash x is either greater than 0 or f dash x is either less than equal to 0 for all x which belongs to its domain. For all x which belongs to its domain, right? So this if a function y is equals to fx is monotonic, then there is no local minima or maximum. Rather than that, we can call it there is no extreme point. right? So don't look out in these cases. But now let's start with the question. And also, yeah, one more point. So we are saying that there is no monotonic function. I mean, for a monotonic function, there is no extreme value, right? But let's say if we are considering a function y is equals to fx, and this is a continuous function on some domain, right? And we want to ask about its minimum and maximum value on a closed interval, right? The example that I have took, right? Example that I have took in this case. For example, from x2 to 7.5, this was a closed interval, right? This was a closed interval. And we have been asked about the minimum and maximum value of this function. In these cases, there will definitely be a minimum and maximum value. Definitely, right? Definitely there will be a minimum and maximum value. I mean, you are talking about closed intervals, right? In that certain closed interval, from when we are talking about this, then we are taking some values for a and b, right? We're not considering the minus infinity to plus infinity domain, right? So this only suggests that um, for a continuous function, there will definitely be a minimum and maximum value. And also, I would like to show you one example here. Let's say I have this. Okay, this is 2 and this is 4. Right? Now I have my line this some line which is basically y is equals to 2. This line is y is equals to 2. Now I'd like to show you this example. So if I want to ask minimum and maximum at in yeah, for x belongs to for all x belongs to 2 to 4, right? Then this function, this particular function, this is a constant function, right? This has 2 throughout 2 to 4. This has 2 throughout 2 to 4. So y minimum is also 2 and y maximum is also 2. So this can happen that the minimum and maximum values are same. So basically a function can be constant. We are not saying that constant is not valid, but definitely there will be a minimum and maximum value. That can be same. It means that the functions are constant. Okay, you're okay with that. But whenever a continuous function is defined in a closed interval a to b, there will definitely be a minimum value and there will definitely be a maximum value that exists for that function, right? That can occur at different points. We don't really we are not concentrating on that point, that what are those points at which these values occur, but we are saying that definitely there will be a minimum and maximum, right? Yeah, chalo, let's I mean, today I don't think we'll be able to complete the question, so let's start questions from next class. Okay. If you have any doubt, if you're feel free to ask. Okay, in that case, we can end the class.
So what does monotonic mean?
Sorry, Tari.
So what does monotonic mean?
I did not understand.
So what does monotonic mean?
Acha, monotonic means either your function is only increasing or your function is only decreasing. For example, if you remember this graph, then